Yeah. Yeah, I'm unmuted. Oh, sorry. Yeah, I'm unmuted. Yeah. Hello, everyone. Good evening. Hope you all can hear me properly. Yes. So yeah. So today we are going to start with what we are today. We are going to start with classification of elements and periodicity in properties. Remember last class we tried to complete the structure of atom and we did discuss some of the questions with related to what? With related to structure of the atoms. Okay. So as I want to tell you a few things that periodic table is the very basic chapter. We should be knowing this chapter because this acts as a foundation and it helps to understand many other chapters, like for example uh, we have some p block elements, s block elements, d block elements, coordination compounds, and many other concepts. So it is very important that we understand the properties, and the main important is the trends in the periodic table. Understanding that is very important. Okay, so in today's class we are going to study selectively few topics with respect to periodic table or classification of the elements in the periodic table. So the first thing what we are going to study is nomenclature of elements with atomic number greater than 100. Okay, so even if you check your last 3 years NEET paper, you will find one question which had come on what, which had come on the uh, nomenclature of elements with atomic number more than 100. Okay, last 3 or 4 years if you check, you'll find a question. And once we are done with the nomenclature of the elements having atomic number more than 100, we are then going to start with what? We are then going to start with trends in periodic table. Trends in the periodic table. So first we are going to start what? We are going to start with the nomenclature of elements with atomic number greater than 100. Okay. So the first thing we have to understand whenever I say the nomenclature, okay, whenever I say the nomenclature, I have to clearly understand the nomenclature is according to what? It is all according to a system which is called as what? Which is called as the IUPAC. Okay, so you can understand, or I can ask you one simple question: what do we exactly mean by IUPAC? Okay, so all these things. So even in your theory exams, they may ask you what is an IUPAC. Okay, so it is International Union of Pure and Applied Chemistry, correct? So this is what we mean by IUPAC. So only they have the authority to give what? They have the authority, and according to them we have to what? We have to nomenclate the elements. Okay, now until the names for the elements more than atomic number more than 100 were decided, IUPAC made a very clear rule that all the elements having atomic number greater than 100, they have to be named according to the nomenclature or according to the system what they have set. Okay, so now let me say I'm going to take an example. So let me say I have an 101 here. Okay, so let me say an element is having an atomic number 101. So how do I name this according to the system? Okay, so now I understand here. If I see the table over here, I understand that for every digit there is a name and there is an abbreviation, correct? So you see for 0 there is nil, for 1 there is UN, for 2 it is bi, for 3 it is tri, for 4 it is quad, 5 it is pent, okay, and so on. And similarly they have given the abbreviations, correct? The only thing you have to be very careful during using these abbreviations is for the 7, because when you see the 7, normally we come across what? Normally we come across hept, but here it is not hept, it is sept. Okay, so you can understand why. I mean, the whole reason why they have kept the sept is because if you see the 6 is hex, which is having an abbreviation of h. Again, if the 7 was kept hept, the abbreviation would have again repeated h. So maybe that is the reason why they have kept here what? They have kept here sept. Okay, so now let us try to understand how do we nomenclate this particular atomic number who's having atomic number of an element 101. Okay, so here I understand 1 is representing what here? 1 is representing UN. 0 is representing what? 0 is representing NIL, and again UN is representing what? It is representing UN. Okay, now once we write all this, there's one basic rule we have to write is while ending the, so you can write it down, while ending the name of an element, while ending the name of element using the above system, we are supposed to use what? We are supposed to use IUM at the end. IUM at the end. IUM. Okay, this is what we are supposed to use. IUM. So here I have an UN. Okay, I have NIL. I have UN, and again I have to end the name with what? I have to end the name by adding what here? I, U, and M. So how do I completely name it now? It will be what? UNNIL UNIUM. So this is what? This is the nomenclature of an element who's having atomic number. How much? Atomic number 101. Okay, so this is the name. Now coming to the abbreviation part. Okay, so now let us try to understand the abbreviation part. So now here UN, just check how do I represent the UN. UN is represented by what here now? It is represented by U. NIL is represented by N, and again here it is U. Okay, so how do I write the abbreviation here? It is going to be UNU. UNU. So this is the symbol. This is the symbol I can say for what, or the abbreviation for an element with atomic number what? Atomic number 101. Atomic number 101. So using this table, we have to try to nomenclate the elements who's having atomic number more than 100. So let us try with another simple example. Okay, let us try with another simple example. Before that, I would give you 30 seconds to complete the writing. So you have 30 seconds to note down the things. This was the system which was used in earlier days to nomenclate the elements with atomic number more than 100. Okay, so I think now if you see up to 118, the elements up to 118 at least, okay, at least 118, we have got all the elements named there. So you can take one as a homework question, like what is the actual name for the element 101? 101. Okay, right, let us go for the next one, a simple question. Okay, so if we have, let me say I have an atomic number over here, an atomic number, let me say I have 1, 1 and 7, 117. Okay, so if I have an atomic number 117, how would you name this element? Okay, how would you name this element and what would be its abbreviation? So I'm going to give you 30 seconds exactly, and your time starts now. You have 30 seconds and your time starts now. Use the table. You need to practice the table. Okay, you need to practice the table so that it becomes easier for you if the question is given on this particular topic. Okay, definitely the NEET has asked this question. There's no doubt in this. Okay, they have asked this question. Okay, so 117. So how do I solve it? So 1 is a representation of what here? 1 is a representation of UN first. Correct. Then again you are having what? Again you are having UN because there's one more 1. Then you are having sept. Correct. For the 7 you have a sept. Okay. For 7 you have sept, and the name should end adding what? Adding IUM. So I can say unseptium. Correct. Unseptium. And what should be the abbreviation for this? For UN, it is going to be U. For UN, again, it is going to be U. For sept, it is going to be S. So the abbreviation is what? Abbreviation is U, U, and S. Okay. So last question on this. So let me say if I have an atomic number, let me say somewhere around 108. Please have an atomic number 108, and how would you name it? And you are having 3 minutes time. You're having, okay, I'll give you 30 seconds time. Okay, 108. So here, how do I write? Here it is UN. 0 is a representation of NIL, and 8, we see it here, right? 8 is a representation of what? 8 is a representation of oct. Then the name has to end by what? The name has to end by IUM. So unnil octium. Unnil octium. UNNIL octnium. Correct? Octium. The abbreviation is going to be what? UN and O. UN and O. Okay. Now it becomes very interesting. It becomes very interesting. So just check how do I solve the next example. Okay. Most of the times we do see students get confused, and let me say I take now the example of, let me say I have 102 here. Okay, so let me say I have 102. So here it is UN, then I understand it as NIL, then I understand it as BI. Correct? Then understand it as BI. Just check this here. Okay, name. But what I have to do is that I have to end the name with what? I have to end the name with IUN. Correct? Now, what I do observe here is there are two I's. While writing this name, I find there are two I's. Alphabets you see there, right? You see there are two I's. Okay. So if there is a name, if there's a name which is having two I, okay, remember this is an IUM, right? So while adding that, if you find one more I here, you can exclude one of the I here. So I can write this as what? UNNIL BIUN. That's it. Uni unnilbium. Okay, unnilbium. So you can exclude one I. And what will be the abbreviation here? It is going to be UN, and for 2 it is what? For 2 it is B. UNB. Okay. No need to include the I 2 times. Instead of that, you can exclude one and simply write it as UNNILBIUM. So same way, let us take an homework question. So let me say you have an atomic number 103. Let me say you have an atomic number. Let me say you have atomic number 103. Okay, so it's like a homework question. So try to nomenclate the molecule. Try to nomenclate the molecule. Okay, so this is all about what? This is all about the nomenclature of elements with atomic number more than 100. Atomic number more than 100. Now, let us try to understand another very, very important part of the periodic table, that is trends in what? Trends in periodic table. Okay. Now, when I say trends in the periodic table, okay, when I say trends in the periodic table, what are those trends, or about what trends I'm actually speaking here? Okay, now you might have heard of atomic size, you might have heard of ionic size, correct? Atomic size, ionic size, then there's an ionization energy, then there's an electron affinity, then there's an electron negativity, correct? So all those things, melting point and even the density, all those things. Okay, so all these characters, we simply call them as what? We simply call them as the trends. Okay, and in today's class, we'll mainly try to discuss few trends. So let me say I'm going to start with the atomic radius. Okay, I'm going to start with the atomic radius. Second thing is I will also discuss today about the ionic radius. Discussing I'm also discussing electronegativity. I'm also discussing electronegativity today. Electronegativity. Okay. And I'm also discussing ionization energy. I'll also try to discuss ionization energy, or I can simply say ionization enthalpy. Okay. So what are the things we are trying to discuss? We are trying to discuss ionization enthalpy, electronegativity, ionic radius, and atomic radius. So let us start with the atomic radius here. Okay. So let us start with the atomic radius. Now, when we see or when we try to imagine the periodic table, so periodic table somewhat looks like this, correct? So if you can imagine the periodic table, so this is exactly how the periodic table looks like, correct? And here you see there are F block elements, correct? So if I have to categorize them or categorize the periodic table, I clearly understand that here I see the S block elements, here I see the P block elements, here I see the D block elements, and in the same D section I also see what actually it is present in between the S and D. Here I also see the F block elements, correct? Now it's a very interesting question to understand why exactly do we call it as an S block element, why exactly do we call it as P block elements, why do we call it as D block elements, okay, and why do we call it as F block elements. So you can take a question like, why do we call it as S block, why do we call it as a P block, why do we call it as a D block, or why do we call it as F block? Okay, so it all depends on the valence electrons entering the particular shell. Okay, so that's also an let me say an homework question. Okay, so now let us now comment about what here. Let us now comment about the first thing is we will start with the atomic radius, or simply I can say atomic size. Okay, atomic radius, or simply I can call it as an atomic size. Now, what exactly do we mean by the trends with respect to atomic radius? Okay, we mean to say that how exactly the size varies, okay, across the period and along the group. So we try to understand here how exactly, okay, how exactly it is trying to behave across the period here. Okay, so I'm just trying to make a point there, how exactly it behaves across the period, correct, and how exactly it behaves along the group. I'm pretty much sure you people already understand what is a period and what is a group. Okay, so now we also try to understand how many periods are there. There are 7 periods, correct? From n is equal to 1 to n is equal to 7. That is what we have studied with respect to periodic table. And how many groups are there? There are 18 groups, correct? There are 18 groups and there are 7 periods. So how exactly the size in the sense, how exactly the atomic size, or in another simple words, I should say atomic radius, how exactly it behaves, or what are the characters of the atomic size with respect to all the elements across the period and along the group. Okay, so how exactly they behave. Now, when we try to discuss atomic radius along the group, okay, and we try to discuss the atomic radius along the group, what exactly is happening, and across the period, what exactly is happening, that is our main question here. Okay, so before we start with the trends, or before we start with the behavior, we have to first understand that the what exactly do we mean by the atomic radius. That is the most important thing, correct? So if you remember, we do have studied Bohr's model of atom, right? So that is what we have studied. So we understand that center there is a nucleus and then there is a shell over here, correct? So this is how the shell, correct? So we have definitely learned this system, correct? This system in our lower standards. So let me say now there is an electron over here, and I would say that this is my outermost electron. Okay, so let me say this is my outermost electron, and I can also say that if I can also say that that is my outermost. So let me say this is my outermost orbit. Okay, the outermost orbit, let us not forget that the outermost electron can be again simply called as what? It can be simply called as the valence electron, correct? It can be simply called as a valence electron, or here I can simply call it as what? I can simply call it as a valence orbit. Okay, or let us keep it as what? Outermost orbit. Okay, so how do I define an atomic radius? An atomic radius, if I have to define, it is the distance between what? It is the distance between the nucleus, which you see here. So this is our nucleus, correct? It is the distance between the nucleus and the outermost electron. It is the distance between the nucleus and the outermost electron. So exactly from here, what is the distance between these two? Correct. I'm just going to remove this one. Let's not confuse ourselves. Okay, so the distance between the nucleus and the outermost electron, we classify them as what? We classify, or we define it as what? We define it as the atomic radius. So if I have to write a definition for this, if I have to write the definition for this, the distance, please write down the definition part. Definition part, the distance between the center, the distance between the center of nucleus, the distance between the center of nucleus and the outermost electron, and the outermost electron. Let us not forget that the outermost electron can be also called as the valence electron. So this distance between the nucleus and the outermost electron, we simply call it as what? We simply call it as the atomic radius. Now, when I say atomic radii, okay, or simply atomic radius, the atomic radii can again be classified into three types. The first one is what? The first one is the crystal radius. We speak it in terms of what? In terms of the crystal radius. Okay, and then second, we speak it in terms of what? We speak it in terms of van der Waal radius. We speak it in terms of van der Waal radius, and also we come across what? We come across the covalent radius. We come across the covalent radius. So these are again what? These are again the classification which comes under what? Which comes under the atomic radii. Now, the next important thing, obviously, I will tell you how exactly the radii of these things vary. So if I have to write how exactly the order of radii is, so let me just make a note of it. So order of radii. Order of radii. So I clearly understand that my van der Waal radius. So please make a note. Van der Waal radius. Van der Waal radius is much, I can write it in a decreasing order. First comes what? Van der Waal radius, then comes the crystal radius, then comes the crystal radius, and the last comes what here? The last comes the covalent radius. Last comes the covalent radius. Obviously, we will try to understand if what happens if there is a decrease in the radius, how exactly it is going to affect the bond strength. Okay, all those things we are definitely going to, or we're definitely trying, we will try to understand. Okay, so this is how exactly is the order of the radii follows. Okay, next thing we have to understand is on what factors does the atomic radii depend on. That's again a very important question. On what factors does the atomic radii depend on? Okay, so factors, or I can simply say atomic radii depends upon. Atomic radii depends upon. Atomic radii depends upon. The first thing is, so what are the factors that depends upon? Okay, atomic radii. The first thing that is nature of bonding. Very, very important. Nature of bonding. Okay, so we if we just check the last point, what we have written, so you see there is a van der Waals radius, you see there's a crystal radius, and you see the covalent radius. So if there's a van der Waals radius, I mean, if there's a van der Waals force of attraction, then the van der Waals radius here is the larger one, correct? But if we think, or if there is a pure covalent bond between them, then the radius is going to be what? The radius is going to be quite low here, correct? So this is exactly how it happens. So it all depends on what kind of a bond is present between the atoms, based on which the atomic radii will vary. So this is our first point. Okay, so let us try to understand the second one. The atomic radii also depends on the oxidation state. Atomic radii also depends on the oxidation state. And the third point, I can say the atomic radii also depends. So here only I can say, even I can link it to what? I can link it to the bond character over here. I can link it to the bond character. And the next thing is, it can also depend on what? It can also depend on the coordination number. It can also depend on the coordination number. Obviously, the oxidation states, nature of bonding, what are the different types of bondings, what exactly do we mean by coordination number, step by step you will be learning. So let's not panic here. Okay, nature of bonding, and also I can say here itself, like how many bonds, even that matters, how many bonds the particular atom is making. So all these things play a very important role in deciding what, and or all these things, they play an influential role. Okay, influencing what here? Influencing the atomic radii. Atomic radii. Now, when we take the periodic table, so let us go back to the periodic table. When we take the periodic table, so what exactly happens here along the group and across the period? So when we say along the group, so let me say I'm going to just roughly draw the periodic table. So let me say this is my periodic table here. Okay, let us say this is my periodic table. So when you go down the group, okay, so I'm particularly mentioning it as what? I'm particularly mentioning it as down the group. So this is down the group, and let me say this is across the period here. Okay, across the period. So atomic radius down the group always increases. So I can write here atomic radius is what? Atomic radius goes on increasing. Goes on increasing. But across the period, atomic radius goes on decreasing. So across the period it decreases, down the group it increases, size goes on increasing. So if you take an example, so let me say I have here, let me say I have, I'll take the first group elements. Okay, I'm going to take the first group elements. So let me say I have here the lithium guy, let me say I have a sodium, I have a potassium. Okay, I have a rubidium here, and let me say I have a cesium. Okay, so they all belong to what? They all belong to first group. Let us not forget that. Okay, they all belong to first group. So if they belong to the first group, so how exactly the size varies here? Okay, so if I want to write the size, okay, lithium is the smallest guy here, correct? So lithium, because down the group it increases, correct? Size increases. Lithium is the smallest guy. Then comes what? Then comes the sodium, then comes the potassium, then comes the rubidium, and then comes the cesium. So this is order with respect to group. Okay, down the group. Okay, the normally what we take, normally down the group, or else I can say in every group, normally what happens, the size should increase down the group. But obviously when you see the periodic table, there are definitely few exceptions, which again, as I told you, no need to panic. When you study one by one, you will definitely understand what are the exceptions, or where exactly you find those variations. Okay, where exactly do you find those variations? So let's not worry about that. Now let us check across the period now. Let us check across the period. So I'm going to take few examples. So let me say I take an example of boron, I take an example of a carbon, I take an example of a nitrogen, oxygen, then a fluorine here. Okay, so You see, across the period, how exactly happens or what exactly happens to the size. So here we were mentioning it with respect to what here, with respect to down the group size. Okay, so this is down the group size. So now let us try to understand what exactly happens across the period now. What exactly happens across the period. So if you check across the period, as I told you that size should decrease, correct? So what happens, what exactly happens here? The boron guy should be what? Should be the biggest atom, then comes the carbon, then comes the nitrogen, then comes the oxygen, then comes the fluorine. So look at the variation of the size, how exactly is the behavior down the group and across the period. So again, I can generalize a statement that across the period in the periodic table, normally what should happen to the size? Normally the size should go on decreasing. So we are speaking about what here? We are definitely speaking about the size. Okay, so the size should what? The size should decrease across the period and increase down the group. Now, what exactly is the reason? What definitely there can be a question, like a true or false type of reason or a statement which is correct, which is incorrect, all those type of questions. So, what is the reason? Why exactly down the group size increases and why exactly across the period size decreases? So that is our main question now. So this can be easily solved using the Bohr's atomic model. Okay, concept of Bohr's model. So let me say if I have a lithium. So let me say if I have a lithium, and let me say if I have a sodium, and let me say if I have a potassium here. Okay. So let us not forget the atomic numbers of these guys. Okay. Let us not forget the atomic number of these guys. We do understand the atomic numbers, right? So okay, so if we try to understand hydrogen, helium, and lithium, atomic number 3, atomic number 11, atomic number 19. Okay, you people have definitely learned writing the electronic configuration. If it is 3, I can write it as what? I can write it as 2 comma 1, correct? For sodium, I can write 2 comma 8 comma 1, and similarly for potassium, I write it as what? 2 comma 8 comma 8 comma 1. Okay, now when you go down the group, look at the shells. What exactly happened to the shells? In your lower standards, if you remember, you people have definitely studied there is a K shell, there is an L shell, if there's an M shell, and there's an N shell, correct? K, L, M, and N shell. So if I have to, give the shells here, so I understand my first shell is always the K. So all these are what? All the first one is always the K shell. Once the K shell is over, then starts which one? Then starts the L shell. So here you will see there's an L shell. Here you will see there's an L shell. Once the L is over, then comes what now? Then comes there is an M shell. Correct? K, L, M, and N. So here there's an M shell, and then you see the N shell. Okay. So what I do understand here is when you go down the group, what exactly happens? The number of shells, so I can make a point here, number of shells increases. Correct? Number of shells increasing. Hence, what should happen? Hence, the size also increases. Size also increases. Because when we see the lithium atom, okay, when we see the lithium atom, so let me say I have a nucleus over here, and this is my first shell, and let me say this is my second shell. This is my lithium atom, okay, having two shells. But when you take the potassium atom, so let me say this is my nucleus. How many shells it has? One. It has a second one. It has the third shell, and let us not forget that it is also having what? It is also having the fourth shell. Correct? It also has the fourth shell. So just look at the size of the shell here. I mean, size of the atom. So I clearly understand that potassium atom is a larger compared to the lithium atom. So what exactly happens? The size is going on increasing. Okay, continuously the size goes on increasing. Okay. Now this is what? This is down the group. Now let us try to understand what exactly happens across the period. Okay. So why exactly the size has size decreases across the period? Because when you go across the periods, what exactly is happening? Atomic number increases, correct? Across the period, I'm saying, okay. atomic number increases across the period, correct? Across the period. Agree with this point? Okay. So we already understand what is an atomic number. Atomic number is nothing but the number of protons, correct? So if protons goes on increasing, what exactly happens? Nuclear charge increases. So let us not forget that. Nuclear charge increases. Now, what is exactly is the nuclear charge? So if I have an center nucleus, okay. So how do I define this nuclear charge? Nuclear charge is the it is an entity which actually attracts the electron, correct? It is the one which attracts electrons. It attracts the electron. Okay. So let me say if I have two scenarios over here. Okay. So let me say there are two scenarios. So here, let me say there are 9 protons, and let me say here there are 6 protons. Okay. And let me say there's an electron. So I have a very simple question. So you have a nucleus with 9 protons and you have a nucleus with 6 protons. So what do I understand? Whose nuclear charge is stronger here? I clearly understand, but that my atom with 9 protons is having a stronger nuclear charge, correct? So stronger the nuclear charge, what exactly is happening? The electron is getting pulled towards this nucleus. So this is called as what? This is called as nuclear attraction. Okay. So greater the nuclear charge, the electron gets inside or comes inside. Okay. So if the electron is getting pulled inside, what exactly is happening to the size? If the electron is getting pulled inside, the size definitely goes on what? Definitely decreases. Size decreases because we have clearly understood that what is an atomic radius? It is the distance from the nucleus to the outermost electron. If that outermost electron, because of the nuclear charge, is getting pulled inside, if it is getting pulled inside, so what exactly happens? The size goes on what? The size goes on decreasing. Simple concept. Size goes on decreasing. Okay. So I'll repeat once again. Down the group, because in the increase in the number of shell, the size increases, and across the period, number of protons, that means atomic number increases, number of proton increases, so nuclear charge increases, and hence what will happen? The electron is pulled more towards the nucleus, and hence the size goes on what? The size goes on decreasing. Size goes on decreasing. Okay. Right. So now let us try to understand the next important trend. The next important trend, that is, let us try to understand the ionic radius. Okay. So before we start with the ionic radius, we have to understand two simple concepts. Okay. Or what exactly do we mean by an ion? Correct. So if I have to, give you a simple definition for an ion, I clearly understand this is what? This is a charged species. Correct. An ion is what here? An ion is a charged species. So you can make a point over that. An ion is charged species. An ion is charged species. That means it can either have a positive charge or it can have a negative charge. If it is having a positive charge, we simply call it as what? We simply call it as a cation. And if it has a negative charge, we call it as what? We call it as an anion. Okay. So when does this ion form? Okay. So there are two conditions. So let me say I have an atom over here. I have an atom over here. So if there is a loss of electron, so let me say there is a loss of electron there. Okay. If there's a lot of loss of electron, then there's every possibility that it forms what? It forms a cation. That means having a positive charge. And if there is a gain of electron, then what exactly is happening? It forms an anion. That means it is having which charge? It is having a negative charge. Atom loss of electron gives you positive ion. Atom gain of electron gives you negative ion. Now, what are we trying to discuss over here? We are trying to discuss about the ionic radius. Correct? We are trying to discuss about the ionic radius. So first thing we have to understand, few simple or few basic things we have to understand. what exactly happens to the size? So let me say if I take this as my parent atom. Okay. So let me say this is my parent atom. And the question is very, very simple. Try to understand it. So if you compare the parent atom, what will happen to the size of the cation? We are speaking about the size of the cation, and what should happen to the size of the anion. So we'll try to figure out what should happen to the size of the anion and what should happen to the size of the cation with respect to what? With respect to the parent atom here. With respect to parent atom. Okay. So let us try to understand the concept. Okay. Let us try to understand the concept. So now let me say I have an atom here. Okay. Randomly, I'm just taking an atom. Okay. Randomly, I'm taking an atom. So let me say this is my nucleus over here. Just give me 1 minute. So let me say this is my nucleus. It's having a nucleus here. Okay. So let me say this is the nucleus. And now what I'm going to do is I'm going to draw a shell around it. So you see there's a one shell here, and I'm also going to, try to draw another shell over here. Okay, another shell over here. And let me say I'm going to place an electron over here. Okay, let me say I'm going to place an electron over here. Now, what I'm actually trying to explain here is the distance between the nucleus and this electron. Correct? The distance between the nucleus, okay, the nucleus and this electron is what? It is the atomic radius. Now let me say if this atom loses the electron, okay, so if this atom loses the electron, which is that electron? The one which was present, the electron which was present over here. Okay, it is the same electron which has been lost. Okay, so what exactly happens if the electron is lost from the outermost shell? Okay, if the electron is lost from the outermost shell, so this is a nucleus. Now it is having only one shell. Correct? Because let us not forget loss of electron. So here, first give me 1 minute. Loss of electron, it is indicating what? It is indicating this is my cation. Correct? Cation with which charge? With the positive charge. Now the problem is what? The problem is the outermost electron has been gone. Correct? The outermost electron is lost. If the electron is lost from the outermost orbit, look at the size of the atom. You're going to count for the outermost orbit now. Correct? Outermost orbit where there's an electron. Okay. So let me say here there was an electron. Okay. So we are going to consider this electron for the atomic radius now. For the atomic radius, or now here I can say it is an ionic radius, because the whole atom has got which charge? The whole atom has got a positive charge because of the loss of electron. So what I do understand is when you compare the parent atom, loss of the electron results in what? Results in decrease of size. Loss of electron results in decrease of size. Loss of electron results in decrease of size. Loss of electron results in the decrease of size. Now let us go for the gain of electron here. Okay, so we'll try to understand what will happen if there is a gain of electron. Okay, so I will write here plus electron. Correct? Gain of electron. So what should happen? So now if there is a gain of electron, so let me say now this is my nucleus and here is my first shell, and let me say there is another shell over here. Let us not forget there's an electron here, there's an electron here. Now the one more electron which comes has every possibility that it stays away and creates its own radius over here. So this is our third electron which is actually getting entered. So let me say I'm just going to mark it. So this electron is here. Okay. So just look at that. What exactly has happened to the size now? The distance we are going to now count between this. We're not going to take the electron in the second orbit. We are going to take the electron in the third orbit. and hence the size will depend on the electron in the third orbit. So this whole atom, because of gain of one electron, gains the negative charge. So let us not forget, this is our anion. This is our anion. So what is going to happen to its size? It is going to be increase in size. So here you see there is a decrease in size, and here you see there is an increase in size. Increase in size and decrease in size. So to solve, again, you can check your past papers. Definitely question on this. They keep on asking. So if I give you a question, so let me say you have a question now. Okay. If you have a question, so let me say I write Mg plus 2, I write Na plus 1, I write here, let me say fluorine atom. Okay, I write oxygen with -2 charge, and let me say nitrogen with the -3 charge. Check the charges. Mg plus 2, Na plus 1, correct? Na plus 1, then you have a fluorine, then you have an oxygen -2, and you have a nitrogen with a -3. Now my question is very, very simple. My question is very, very simple. What should happen? What should happen to the size, or you can arrange them in increasing order of the size. Okay, I'm going to give you exactly 60 seconds to solve it. You have 60 seconds. Right. So how do I write a simple statement? Okay. So compared to the parent atom, comparing parent atom and an anion of that atom. Okay. So I clearly understand the size of this guy is smaller than the size of the anion, correct? Simple statement here. And similarly, if I compare the parent atom, along with its own cation, then I clearly understand that the size of the cation is what? The size of the cation is the smaller one. The size of the cation is the smaller one. So this much I have clearly understood, correct? So what I can make a statement over here is, okay, greater positive charge, statement, greater positive charge. Okay, so here greater positive charge. Please give me 1 minute and make some corrections over there. Greater positive charge. So let me say you have a greater positive charge. Okay, greater positive charge. What should happen to the size? Size goes on decreasing. Greater positive charge, size decreases. Greater negative charge, what should happen to the size? Size should go on increasing. So let us not get confused regarding it. The size goes on increasing. The size goes on increasing. So I clearly understand now who is having a greater negative charge here. The nitrogen is having a greater negative charge, right? So N-3 should be the larger molecule. Then comes what? Then comes the -2 guy, correct? Then comes the -2 guy. Then I can write the fluorine guy here. Okay. Then comes the Na plus 1 and the Mg plus 2. Mg plus 2. Okay. So simply I can simplify this. I can simply write it as what? If we consider the anion is slightly larger. Then comes the atom, normal neutral atom, and finally comes what? Finally comes the cation. Simple statement to solve the competitive questions. Right. Now, as I told you, no, when we go to the atomic radius and when we go to the ionic radius, we have just discussed what? We have just discussed the normal trend, correct? What happens across the period, what happens along the, I mean, down the group, what happens, that is what we have studied. But as I told you, when you start studying in detail regarding the S block elements or P block elements, T block elements, and F block elements, definitely you will come across what? Definitely you will come across few of the exceptions, or I should say some of the variations. Okay, it exactly does not follows that down the group size increases. It may not follow that across the period size decreases. It may not follow. So there are definitely what? There are definitely some variations. Definitely there's a variation. So here what we will do is, and we will try to study the transition and inner transition elements first, or else I should simply say D and F block elements. D and F block elements, D and F block elements, atomic radius. D and F block elements, atomic radius. Okay. So now if I take, so let me say the D block elements. Okay. If I take a D block elements, if I take D block elements, normally we write them as what? We write them as n-1 D. Okay, all these elements. So if I take right from scandium and go up to the zinc, okay, I'm taking it from scandium up to zinc. So I do understand what is the atomic number of the zinc. The atomic number of the zinc is 30. Okay, potassium is 19, calcium is what? Calcium is 20. So scandium is how much here? Scandium is 21. So when you see the sizes from scandium to the zinc. So if I try to draw it, when you see the sizes from scandium to the zinc, so let me say here is my atomic number. Okay, so let me say here is my atomic number, and let me say here is my size. I'm speaking with what? Let me say I'm going to speak with my atomic size. Okay, so across the period, right? So I'm speaking about across the period here, correct? So this is all with respect to what? This is all with respect to across period here, correct? It's all across period. So what should happen actually across the period? The size should what? Normally the size should decrease, correct? The size decreases. But when we see the graph of the transition elements, okay, when we see the graph of the transition elements, so this is exactly how the graphs looks like. So it slightly goes on like this. Look at the variation, slightly goes on like this. Look at the decrease in the size. It's still decreasing, it's still decreasing. And then slowly when you come towards the zinc, the size goes on increasing. Okay. So here you can say there is a zinc, and here you can say there is a copper. Okay. Copper is atomic number 29. Copper is 29 and zinc is 30. Okay. And it comes like this: scandium, then you have a titanium, vanadium, chromium, manganese, okay, iron, cobalt, nickel, all those things. So you just check the variation here. Okay. First, according to the general statement what I gave, that the size goes on decreasing, so you see that there is a size definitely decreasing. No, absolutely no doubt in it, the size is definitely decreasing. But when you come to the copper, and then when you end it at the zinc, whose atomic number is 30 and copper is 29, slowly what is happening? Slowly at this particular area, what exactly happens? The size goes on increasing. The size goes on increasing. Now, what should be the reason for that? Okay, what should be the reason? The whole reason why the size, give me 1 minute, The whole reason why the size goes on increasing is because of an effect which is called as a shielding effect. In some of the textbook, they have also used a term called a screening effect. So screening effect, shielding effect are both same. So absolutely no need to get confused. Shielding or screening both are same. Shielding or screening. Okay. So what exactly do we mean by the shielding effect, or what exactly do we mean by the screening effect? Okay. So what exactly do we mean by screening, or what exactly do we mean by the shielding effect? Okay. So let us try to understand what exactly is this screening effect now. Okay. Just give me 1 minute. What exactly do we mean by the screening effect? Yes. So now let me say there is a nucleus and there are shells and there is one more shell, and let me say the electron is sitting over here. Let us not forget that in all these cases also you will find what, and I mean in all those shells also you will find what, you will find the electrons. I'm just randomly drawing the electrons. Okay, I'm not considering them as a K shell, L shell, M shell, all those things. I'm just randomly drawing the electrons. Let us say they are present in the shell. Okay. Now, what should happen here? The nucleus should try to attract this electron, correct? The nucleus should try to attract the electron. So let me say my first point is what? My first point is nucleus should attract electron, correct? Or I can say outermost electron. Okay. But during this entire process, where the nucleus attracting the electron is blocked by what here? It is getting blocked by the electrons which are sitting over here. Okay. So I can simply say, what is this? This is blocking of attraction. So this whole effect is what here now? This whole effect is blocking of attraction. It is blocking of attraction. Which attraction I'm speaking about? The attraction of the nucleus to the outermost electron. So this is blocking of attraction. The blocking of attraction of an outermost electron towards the nucleus, this we normally regard it as what? We regard it as a screening effect, or simply we can call it as what? We call it as a shielding effect. It's either screening or it's either shielding. Okay. So no need to again get confused. What are these two different terms? They're the same terms. Either it is a shielding effect or it's a screening effect. Okay. So what do I understand? If my screening effect, if my screening effect is stronger, okay, if my screening effect is stronger, that means what? If my blocking of attraction is stronger, electron moves far away, correct? Electrons move far away. If the electron move far away, what should happen to the size here? Okay, the size should increase. That is exactly what happening in the zinc atom. The electrons which are present, okay, the 3D electrons, I should say, what exactly they are doing there? They are doing a very good shielding effect, or they are doing a proper shielding. So if the shielding is good, or if I say the screening is good, so what exactly happens? The electrons move away from the nucleus, and definitely what happens? The size goes on increasing. So that is what exactly is happening to the zinc atom. Okay. So this is all about the atomic radius and the ionic radius. Okay. Definitely, there are again few trends that will be discussed in the next class along with the questions. So if you have any doubts, please let me know. Have any doubts, please let me know. Right then, everyone, thank you so much for attending the class. Thank you, everyone.